In this module, we're going to review molarity. I'm talking about how to determine concentrations of a solution, and we'll also review a few other ways of determining concentration and a few other units that are applied to concentration of solutions. More importantly, we're going to take a look at molarity, molality, and then mass percent of a solution. We should be very familiar with molarity already, and molality is probably new to us, but we're going to take a look at those calculations as well as determining mass percent of a solute in solution. Right, so molarity should be very familiar to us because we've talked about moles, right? We know how to calculate moles. Moles equals how many grams do I have over the molecular weight, right, of that substance. Taking moles and turning it into a concentration gives us molarity, where molarity is how many moles of that solute do I have in what's the volume of that solution. There's one downside with molarity, and that's it's tied to temperature and volume. And so taking a look at these two volumetric flasks, if I have the volumetric flask, and let's say this is 1 molar, and then I heat that solution up from 25 degrees to 55 degrees, as we know, when I heat something up, right, the volume expands. The volume's going to increase. And so if I calculate molarity as moles per liter, and my volume changes, right? My volume increases. Well, that means this 55-degree sample will have a different molarity. It'll actually have a lower molarity because my volume just increased. Because of that dependence on the volume and how volume can change over a range of temperatures, we need another way to calculate and look at concentration. That second way is molality. Molality is how many moles of solute I have per kilogram of solvent. Moles of solute per kilogram of solvent. And this is important because this gets us away from the dependence on volume. So my volume could change, and if my volume changes, right, as long as my mass of that solvent stays the same, my molality will stay the same as well. So molality, and that's lowercase m, equals the moles of solute divided by kilograms of solvent. And so taking a look at that same sample, right, molality is moles over kilograms of solvent. Here's my sample, and let's say this is 1 molal. I heat that sample up from 25 degrees to 55 degrees, and sure, that solution expands, so my volume increases, but the mass of that solvent will stay the same. Just because the volume increased does not mean I'm going to see a change in the mass of that solvent. So as a result, both of these will have the same concentration with respect to molality. They could both be 1 molal because the molality of a sample is not impacted by a temperature change of that sample. Because the mass of that solvent is not changing. So here's a sample calculation for you. I've got a solution that's made by dissolving 4.35 grams of glucose, which is 180.2 grams per mole, in 25 milliliters of water at 25 degrees C. Calculate the molality of glucose in this solution. And I even gave you the density of water, but for the most part, you should know the density of water is 1 gram per milliliter. So I have 3 steps in this calculation. The first step, ultimately I need to find molality, which is moles of solute per kilogram of solvent. So a few things I have to do. First, I have to find moles, right? I have to find moles of glucose. Well, I've got 4 0.35 grams of glucose. And I know from the molecular weight that if I have 180.2 grams, that would be 1 mole of glucose. So taking a look, right, grams cancel out, and I'm left with approximately 0.024 moles of glucose. So now I've done part 1, I've found moles of glucose. Part 2, I need to find the mass of the solvent in kilograms, right? So I need to convert 25 milliliters into kilograms. And so if I have 25 milliliters of water, I know that the density of water is 1 gram per 1 milliliter. Milliliters cancel out, so I have 25 grams of water. One more unit conversion, I know I have 1,000 grams in 1 kilogram. And again, my grams will cancel out, and I'm left with approximately 0.025 kilograms of solvent. Now for step 3, the last step, now I can calculate the molality of the solution, right? Because now I know the number of moles. I have 0.024 moles of glucose, and I have that amount of moles dissolved in 0.025 kilograms of water, which is my solvent. And that gives me a molality of approximately 0.96 molal. Right, so 3 different steps we had to take there, right? The last step being the main question that we were asked, but in order to do that third calculation, first we had to find moles, and then I had to convert my volume into a mass in kilograms of my solvent. And then once I'd done step 1 and 2, then I could do step 3. I could determine the molality of this solution. The next term of concentration is mass percent of a solute, and as the name implies, it is the percent mass of a solute in solution. Right, so how do I find the percent of anything? How much do I have divided by the total times 100? How do you find your percentage on an exam? How many points did I score divided by how many points are in the exam? Multiply that by 100. So the same calculation for mass percent. What is the mass of my solute that I'm looking for? What is the total mass of the solution? And that's a key there, the total mass, right? Total mass, this is a little bit different than molality, where we just looked at the mass of the solvent. Here we're looking at the total mass of the solution. The total mass equals the mass of the solvent plus the mass of the solute. Right, we need to know the total mass of the solvent plus the mass of what is dissolved in the solute, right? So here's a sample calculation for mass percent. I've got a solution that's made by dissolving 13.5 grams of glucose in 0.1 kilogram of water. What is the mass percentage of solute, the solute being glucose, in this solution? Well, mass percent of glucose equals how much mass of glucose do I have divided by the total mass of solution. All right, we can't forget this total mass of solution times 100. So one thing to do before we start this calculation, right, my mass of water is in kilograms, my mass of glucose is in grams, so I need to convert my mass from grams into kilograms. So I have 13.5 grams of glucose, and I know that there are 1,000 grams in 1 kilogram, so I have 0.013 kilograms of glucose. My total mass, now that I both have the same units of mass, right, I've got 0.1 kilogram of water plus 0.0135 kilograms of glucose. My total mass is the sum of those two masses. My total mass would be 0.1135 kilograms. Now I can find the mass percent. So I have approximately 0.0135 kilograms of glucose in a total mass that weighs 0.1135 kilograms times 100, right? And that gives me about 11.9% glucose by mass. And we should be able to do this for water as well, right? So if I've got 11%, almost 12% of this sample is the mass of glucose, right? That means that 88% of this sample needs to be the mass of water, right? The whole thing needs to add up to 100%. So 12% of this sample is glucose. That means 88% of the sample would have to be water. The last term of concentration that you will come across, especially if you work in engineering, environmental engineering, or in the field of environmental science, would be part per million, part per billion notation. And so all this is it's a way for us to talk about really small concentrations in a way that's a little bit easier to understand. And that's how we see, environmental contaminants, environmental pollutants, or something that's toxic to us. If we're looking at a toxicology report, it's often given in parts per million or parts per billion, because we understand those numbers a little bit more easily than we understand the actual magnitude of that number. So part per million, what that would mean is the total mass of your solute divided by the total mass of solution, but it's on the order of 10 to the 6. And that comes out to be about approximately 1 milligram per kilogram. So if your contaminant that you're looking at, or if the solute that you're looking at is there in a magnitude of 1 milligram per kilogram, that is equivalent to 1 part per million. And just to give you an idea of how small these measurements are and why it makes sense to talk about them as parts per million instead of something that's 10 to the 6th, right, would be about 32 seconds in a year. That is the level that we're talking about at the parts per million scale. The part per billion is now 10 to the 9th, but it's the same terms. Basically, the mass of your solute divided by the total mass would give you something on the order of 10 to the 9 magnitude. So now we've gone from 1 milligram, right? We've gone a factor of 1,000 over farther. Now we're talking about 1 microgram per kilogram for a part per billion. And so this is something now on the scale of 3 seconds in a century, right? An incredibly small amount. But if we're talking about something that's dangerous, we're talking about something that's poisonous to us or toxic, hazardous that we do not want to be exposed to, often that small amount is more than enough, right? So even though it seems like not a lot, sometimes things on the parts per million and even parts per billion scale can be dangerous. Another way of thinking of these concentrations, right, if you didn't get that from the name, is that part per million basically means I have 1 part per million. So I have 1 part of this solute per million parts of the sample. And the same for parts per billion. I have 1 part of this solute per billion parts, right? 1/1,000,000th of the sample is parts per billion, or 1/1,000,000th of the sample would be parts per million. When we looked at the Flint, Michigan lead crisis, we were talking about measurements on the scale of parts per billion. And so the EPA regulates lead at approximately 15 parts per billion. So that means I have 15 parts of lead in an entire sample of 1 billion pieces, right? So that's the measurement. We don't want to see anything above 15 parts per billion, and some of the houses that they were looking at in Flint, Michigan were as high as 10 and 12, even 13,000 parts per billion. So well above that measurement. But just to give you an idea of how small that is, could you imagine counting out 1 billion things, 15 of them being lead, and that's our minimum, right? That's our cutoff for what we do not want to be exposed to. And as you can see, some houses in that area were well above that measurement.